Okay, we're going to continue on here. Last time we did finish up chapter 14, which was about buffers and titrations. And a reminder again, we do have a quiz on that on Wednesday. So we can do that on Wednesday. So as I mentioned last, yeah, only 14. Yeah. So as I mentioned, 14 and 15 are usually the ones to give people a really hard time in this class. So think if we were on the top of the roller coaster here, maybe coming down. So we're gonna hit 15 here, which is really not a super long chapter, but there's a lot of kind of stuff in here going on. So in chapter 15, we're gonna talk about a couple other sort of equilibrium sort of constants. We're gonna talk about KSP, which is the solubility product. We'll also talk about KF to add to our ever-growing list of K values, which is more for complex ions. So let's start with KSP. And KSP is the solubility product. It is really the equilibrium sort of constant for things that are really considered sort of insoluble. So if you remember your solubility rules, something like silver chloride is insoluble. Um, Now, one of the things that we maybe don't learn so much in the first semester in terms of solubility is the idea that sometimes we do think of solubility rules as being perfect, and it always happens in that case. But there is a lot of things that can affect the solubility of something. There's a lot of factors that play into whether or not you'll actually see, for example, the solid form or not. Even if the solubility rules say you should see a solid, some of those things we're going to talk about in this chapter, like concentration of the ions that are floating around, also, pH is a really big factor, common ion. So there's a lot of factors that can affect whether or not, you will actually, for example, see that solid form, even though the solubility rules tell you that that thing is insoluble. Another idea that may be a little bit new as well is when we do think about solubility rules, and we do think about something being insoluble, even things that are insoluble have some degree of solubility. They're able to break apart in solution a little bit, not a lot, which is why they are considered insoluble. But something like silver chloride, when you do have it in solution, will set up an equilibrium and break apart thinking into silver ions and chloride ions. Again, the equilibrium here, as we will talk about, will really lie a lot to the left here, where it's all together as silver chloride in the solid, but some of it will break apart into its ions. And because it's able to set up this equilibrium, we can write obviously an equilibrium expression for it, just like any other equilibrium expression, which is basically our products divided by our reactants. Now, as you can see here on our reactant side, it is a solid, which means typically speaking, when you write KSP sort of expressions, it's really just the products. And that is because they are always sort of set up this way, solid on the sort of left-hand side of the arrow, or the reactant side, and aqueous ions on the product side. So really, when you do write KSP, pretty much it's always going to be the products. So we do it just like we do any other equilibrium expression, because frankly, it is just another equilibrium expression adding to our list of whatever we got there, KW, KC, KP, KA, KB, all those things. So now we have KSP to join the mix here. Obviously, if we did have some coefficients here, we would take it to the coefficients like normal. Um, as you can see in these examples here, again, magnesium fluoride, they've got a 2 here, so just like normal, we take it to a 2 here, to 2 there, a 3 and a 2, a 3 and a 2. So the KSP, again, as I mentioned, you could think of as being an equilibrium constant for things that are considered insoluble based on solubility rules. I would say if you don't know your solubility rules, perhaps that would be a good thing to review. But there is a lot of information usually in these type of problems that will kind of help you decide probably what to choose and go in the right path, even if you maybe don't really know a lot about your solubility rules, but you may want to maybe review those. Another situation that does occur with KSP is We could also have Q, and Q is the same Q that we talked about previously. Q is calculated the same in this case as KSP. Our Q, just like before, means we're not really sure it's at equilibrium or not, but basically in this particular case, we could use Q and compare it to the KSP to help us decide whether or not we would expect a precipitate to actually form. So if Q is less than the KSP, we have an unsaturated solution. An unsaturated solution is a solution where you haven't hit the maximum amount of solute that will dissolve at that point. So we would expect no precipitate to form. Again, if you put Q on the left-hand side, it goes opposite the way it's pointing. Opposite side are ions, and they should be dissolved. If you have Q is equal to the KSP, you basically have a saturated solution. A saturated solution is one, hopefully you remember, is basically the point where no more solute will dissolve at that temperature, right? You basically got in there everything that will dissolve at that particular temperature. I say temperature because solubility is based on temperature and does change with temperature. So as temperature increases, typically you get more solubility of solids and liquids. As it decreases, you get less solubility of solids and liquids. But a saturated solution would be reached if they do equal each other. If Q is greater than the KSP, you will have a supersaturated solution. A supersaturated solution is one where you have actually way too much solute dissolved in the solvent, and that typically means that the solute wants to come out of the solvent and form a solid. So you would expect a precipitate to form. And again, if Q is on the left and K is on the right, opposite of where it's pointing, that goes to the reactant side where you would expect a solid to form. So um, I would say in most cases, Q is either greater than or less than K is usually what you'll kind of come across in the situation. And you can use that to determine, again, would you expect a precipitate to form if you sort of mix some of these things together? Here's a table of KSP values, and you have a similar table in your book. But one of the things that you will notice about KSP values are they are extremely small. So a lot of them are really, really small values. And again, that makes sense if you think about it, because again, if we have a small value of K, even a KSP value, which is really just a K, that means when we reach equilibrium, we should mainly have reactants. And in this type of reaction, as I mentioned before, it is solid to aqueous ions. So that means with these small values, it's pretty much going to stay together, and you would expect a solid to form. But again, as I mentioned, a little bit of it will break apart. So with KSP values, they typically are really small sort of values when you do those calculations. As we'll see a little bit later on this chapter, when you get to KF, for example, they're actually the opposite. They're pretty large sort of values. So these are very small to keep them together. And that's why, again, it's considered to be fairly insoluble. Again, here you can see things like to the minus 54, minus 47. So a lot of them are really, really sort of small values. When we talk about solubility, that is the amount typically if something is soluble, one thing will dissolve in another. And when we talk about solubility, there's kind of two types of solubility that we kind of come across in this chapter. There could be others, but these are the two major ones. One is known as the molar solubility, and that's the number of moles that will dissolve in a liter of a saturated solution. That is a fancy way of saying the molarity, basically. Yeah. So when you're asked for the molar solubility of something, you're basically asked for the molarity of that thing. The other one is sometimes just referred to as solubility in grams per liter, and that is the number of grams you could dissolve with that solute in a liter of solution. So these are two very common sort of solubility units that we come across in this short chapter. And hopefully also you remember how you could go from one to the next. So if you have moles per liter, but want grams per liter, once again, it is the molar mass there from the periodic table that allows you to get to that area there if you multiply it by the molar mass. So The molar mass is oftentimes used here to go between the molarity and the solubility in grams per liter. Now, there's really kind of two types of problems that you come across when you do these type of problems. And one really does require you to do an ice table. The other one, technically speaking, you can kind of avoid the ice table if you don't want to do it. But I would also recommend, even in the other situation, to still kind of do an ice table because people make a lot of mistakes in these type of calculations. And we'll talk a little bit about those as we go through it. But one type of problem that you are asked to do is to find, for example, the KSP value for a substance. And what you are typically given in that case is the solubility of the compound. And by the way, the solubility of the compound could be in any unit. It could be grams per liter, it could be, milligrams per milliliter or something like that. It could be really in any type of unit. Whatever unit that solubility is given to you in, you do want to get it really into the molarity, the moles per liter. And once you do that, you can figure out the molarity of each ion, and then you can plug it into basically the KSP expression and get an actual value for the KSP. So for that type of problem, technically speaking, you don't necessarily have to do a ice table if you understand molarity and ion concentrations. The second type of problem, which is very common, is you are just given the KSP value and that's it. Or you got to go find the KSP value in a table and you're not given any other information, no other numbers, pretty much just like what is the solubility of this compound, basically. And if the KSP is given to you in the problem, obviously you can use it. If not, you may have to, like I mentioned, kind of go and look it up in a table. At that point, you should do an ice table. And when you do solve in that ice table, that will give you the solubility of that product, the molar solubility, and then you can use something like molar mass if necessary to take the molar solubility to something like grams per liter. So again, as I mentioned, I would probably recommend maybe the ice table for both. There's a lot of situations here where, for example, you need to multiply by 3 and also cube it. And sometimes when people do these problems, they go, well, I cubed it. I don't think I have to multiply it by 3, or I multiplied by 3. I don't need to cube it and stuff like that. So sometimes with the ice table, you can kind of see, oh, yeah, I need to multiply it by 3, and I also need to sort of cube it and stuff like that. So it's a good idea to maybe do it for both. So let's take a look at an example together just to kind of run through how we would sort of work a problem like this. The solubility of silver phosphate, big dramatic pause there. I'm not sure why. So away there, big old space. We'll put it together. 25 degrees is 1.6 times 10 to the minus 5 moles per liter. We're looking for the KSP here. So in this case, we are looking for the KSP, which means you really actually maybe don't need to do an ice table, but we're going to do it just to sort of show you a few of the different things that we do in these type of calculations with the ice table. So the first thing that again, if you're not sure about your solubility rules or things like that, is if you're asked for a KSP, you could consider this guy insoluble in solid. So that's a good way to know that. So we will start with this guy breaking apart into its ions. So remember that when you write these equations, our reactions on the reactant side is always the solid. On the product side is really just these guys breaking apart into the appropriate ions. So we would get 3 silvers and a phosphate in this case, bless you. That would give us a KSP expression of our products over our reactants, but again, our reactants are solid, so they will not be included. So that'll give us silver cubed times our phosphate here. So when we do an ice table here, we're going to kind of do it like normal. We're going to go initially, we are not mentioned obviously about anything of these guys here, so we could safely assume 0. Once again, we're pretty much going to ignore the reactant side because it's a solid, so it's not included in anything here, so you don't have to worry about anything on that side. Now, the change here, we would normally go, right, minus x on the left there, right, some plus x's on the right. With this type of ice table, we actually a lot of times do not use X. We use a different letter just to mix it up, I think. We use S, and S actually stands for the molar solubility. It is basically the molarity. Yeah. So instead of X, I mean, technically you can still use X if you like, but a lot of times people will use S in these tables. And again, when you see that S, it stands for the molar solubility or the molarity, basically. We do it just like we do with X's, which means, again, if we have a coefficient, we got to take that into account. So that's a plus 3S and an S. At equilibrium here, 3S and S. First off, any questions on the ice table there? All right. So like normal, we would take the equilibrium line, put it into our KSP expression, and this would get us, if we take this guy and pop it into there, maybe I'll go down here. That'll get us 3S, and as you guys see from my expression, I still need to cube it times S, and that equals my KSP. Now, at this point, if you had a problem where you were given the KSP, you would solve obviously for S in this case, and that would equal your molar solubility. In this particular problem, we're actually looking for what the KSP value is, so clearly we can't put it in there and use the KSP value to solve for it. So if we go back to our problem, though, it does tell us that the solubility, and this is moles per liter, which means that is the molar solubility of this guy is 1.6 times 10 to the minus 5. That means technically S in this case is 1.6 times 10 to the minus 5 molar. So at this point, what we need to do is basically just put that into our expression on the bottom. That would give us 3 times 1.6 times 10 to the minus 5. And again, you still need to cube it times 1.6 times 10 to the minus 5. And that's going to get me here. Looks like about 1.8 to the minus 18. Let's go up here. 1.8 times 10 to the minus 18 there. Minus 18 as my KSP. First off, any questions on that there? So the reason I would recommend, even in a problem like this, where technically you don't really need to do the ice table, is I can't tell you how many people will do this. And like I said earlier, go, oh, I multiplied it by 3. I don't need to still do that part of it, right? So a lot of people will always kind of screw that up on these calculations. Either they'll cube it and not multiply it by 3, or multiply it by 3 and not cube it. So again, if you do kind of the ice table, you can kind of see, oh, I do need to take 3 times that number. So you can visually kind of see it. If you understand molarity, the reason I said you don't have to necessarily sort of do the ice table is you could sort of do it without the ice table, but it's kind of the same thing because you could just do this as well. So if you understand molarity, as we've talked about, like this guy's molarity is 1.6 times 10 to the minus 5 molar. This would be 3 times that to get the concentration of our silver. That is a 1-to-1 relationship, which means this guy would be 1.6 times 10 to the minus 5. Now you could just go straight into here and get obviously the same answer. It's basically doing the ice table. But again, the ice table might help you do that if you don't mess it up in that sort of case. Yeah. 1.6 times 10 to the minus 5 is the concentration of that whole thing, silver phosphate. But when it does go in for a swim, it's going to break apart into basically you get 3 to 1 as the silvers. So it's 3 times as concentrated in terms of the silver ions. That's why you have to multiply it by 3. And it's basically like a 1-to-1 relationship for the phosphate. So that's why that guy is just 1. So those are technically the equilibrium concentrations, what you would have. What I just did there at the end is technically what the equilibrium concentrations would be at that point. Yeah. So again, I would recommend doing the ice table because again, it just sort of allows you to kind of visually see. I need to multiply it by 3 and stuff like that. And you know, how to maybe guess what you should do. It's a really good move on that. Other questions? Now, by the way, when you do solve for S, S is the molar solubility, and it typically is the molar solubility of the whole thing, like the silver phosphate. So when we solve for S, or we're given that S of 1.6 times 10 to the minus 5, that is really the molar solubility of the silver phosphate. But because it is a 3-to-1, the concentration of silver ions at equilibrium is 3 times that number if you're asked that question. And if you want the concentration just the phosphate, it is 1.6 times 10 to minus 5. So there are some different sort of questions sometimes you're asked. You may be asked, you know, what is the concentration of phosphate at equilibrium, or what is the concentration of silver ions? The phosphate would be the same as the whole thing, but the silver you would have to adjust by multiplying by 3 if you're going to give that answer. Any questions on that there? All right, so why don't you try one here? What is the solubility of silver chloride in grams per liter? Give you some values here that might be helpful. Silver is 107.9, I think. And chlorine is 35.45. All right, so take a few moments, calculate up the solubility of silver chloride in grams per liter if the KSP value for silver chloride is 1.6 times 10 to the minus 10. Okay, let's take a look. So this would be a case where we're given pretty much not much but the KSP. So this is definitely a situation where you should definitely do in the ice table. We want to start with this. Once again, if you're not sure about your solubility rules, if you see a KSP associated with it, it is safe again to assume that thing is a solid and insoluble. So we'll take our silver chloride. It will break apart in this case into a silver ion and a chloride ion. Once again, we're going to KSP that up there. A little silver times our chloride. And that will equal our 1.6 times 10 to the minus 10 in this case. Here we do need to do an ice table. So we will start with 0 and 0. Our change here going to be plus S and plus S. That means at equilibrium here, we will have S and S. Any questions on that so far? All right, so in this case, we do have the KSP, so we basically going to solve it just like we would solve for X. So we're going to take our equilibrium and go into here. That's going to give us S squared is equal to 1.6 times 10 to the minus 10. Obviously, we're going to square root both sides there. And that's going to get us here the square root of 1.6 to the minus 10. Going to get us a 0.00000126 as our molar solubility. That again is basically our moles per liter of silver chloride. Now, this value that we just got here is really our S value. It is also, if we were interested in the concentration of the chloride ions floating around in molarity, it would also be our 0.00000126. Also, that would be our solubility, our concentration of the silver ions that are floating around in that solution. And really, when you do solve for S, it is also the solubility of the whole thing in this case, really, because as you can see, it's a one-to-one relationship backwards. So we end up with the same number if we're doing some stoichiometry. So with that being said, we're looking for it in grams per liter. So to go from moles per liter to grams per liter, we need the molar mass of silver chloride here. So we're just going to add these together. And that's going to get us here 143.35 grams per mole. We're going to use that as our conversion factor here, 0.00000126 moles per liter. We're in this case going to multiply by the molar mass from the periodic table, 143.35 grams per mole for our silver chloride. Moles are going to cancel. And in this case here, we're going to end up with a 0.00, call it 18 grams per liter. That would be the solubility here of silver chloride, basically in water, basically is what the solubility of it is. Is that a lot of solubility? That is not. It basically says you could dissolve 0.002 grams of silver chloride in 1,000 milliliters of water. And that's why we consider silver chloride to be typically insoluble in that case. Yeah. Any questions on that there? Yeah. So let's take a look at another one. Why don't you give this a go? What is the aluminum concentration here? Again, I'm not sure why it's so spread out here. Bring everybody back together. The KSP of aluminum hydroxide, 2 times 10 to the minus. Okay, let's take a look at this one. Again, we're given a KSP, so we do know insoluble here. So we'll start with our ice table here. Again, just going to break this guy apart into its proper ions here, which is aluminum. And once again, here we do get 3 hydroxides in this case. That's going to give us a KSP expression of aluminum times our hydroxide. Once again, here we do need to cube it because of the coefficient that is there. And that would equal 2 times 10 to the minus 32. Again, in this case, if you're given the KSP, definitely should roll some ice table action here. So we're going to go 0, 0 change here. Going to be plus S. Once again, we do need to take the coefficient into account. So that's going to be plus 3S. And that's going to give us at equilibrium here, S and 3S. Any questions on the table here? So as we've been doing, we're going to then take this into our expression, and that's going to get us here. And I'll go down here. That's going to give us S times 3S. Once again, we do need to cube it. Equals 2 times 10 to the minus 32. That is going to get us here S times 27S cubed. Remember, you do need to cube the number, not just the S, which is a very common error people make. So 3 times 3 is 9 times 3, 27 there. That's then going to get us 27S to the 4th is equal to 2 times 10 to the minus 32. We're going to divide here by 27, and then we're going to actually take the 4th root, right, as we do that. And if you do all that good stuff there, so we take 2 to the minus 32 divided by 27, and then take the 4th root of it. Gonna get us a S value here of 5.2 times 10 to the minus 9 molar. Remember, that is the molar solubility. If you're not in scientific notation, then you got a bunch of zeros and probably a 5 at the end of your calculator there, as your calculator probably ran out of room. So that's okay as well. Reminder that if you're not sure, you got to take the 4th root. If you have a button on your calculator like that, you could use that. If you don't, you could caret parentheses 1 divided by 4 would do the 4th root. Or 1 divided by 2 would do the square root. 1 divided by 3 would do the cube root. So you take 1 divided by whatever root you want. You can use a little caret button or on your calculator like X to the little box type of thing. All right, so that does give us the S, and in this case, we were interested in what the aluminum concentration was, and the aluminum concentration in this case of aluminum ions in that solution would be 5.2 times 10 to the minus 9 molar. By the way, if I wanted hydroxide's concentration, which it obviously did not ask for, we would actually need to do 3 times S. So for hydroxide, its concentration would be 3 times 5.2 times 10 to the negative 9. And that would get us something like, it looks like a 1.56 times 10 to the minus 8, or 1.6 times 10 to the minus 8 molar, which, by the way, since that is hydroxide, if I was curious of the pH of this solution, right, I could also calculate the pH of this. I could get the POH by taking minus the log of 1.56 times 10 to the minus 8. And that would actually get me, in this case, a POH of like 7.81. I could then subtract 14 and get my actual pH in this case. And the pH of this solution, the way it sits in water, would actually be a pH of 6.19. Yeah, slightly acidic, actually, even though it's got hydroxide, because aluminum's a little amphoteric type action happening with it. Any questions on that there? So again, if I wanted the molar solubility of aluminum hydroxide, that again would be the S value in this case as well. So that would be what the S value would be for the whole thing. Any questions on any of that there? Okay. So let's talk a little bit about using KSP values to help us decide, for example, if we have a bunch of salts to sort of choose from, and we want to know, for example, which one might be more soluble, which one might be least soluble. Can you use the KSP values to let you do that? You can, in a certain situation, just straight up look at the KSP values to determine which one should be more soluble, which one should be less soluble, if the salts break apart into the same number of ions. So for example, if we took silver iodide, copper 1 iodide, and calcium sulfate here, when we look at each of these here and we break them apart, we get a silver ion and an iodide ion. When we take our copper 1 iodide and break it apart, we get a copper ion and an iodide ion. And when we take a little calcium sulfate, we get a calcium ion and a sulfate ion. So each one of these all break apart into a grand total of 2 ions on the product side. So because they break apart into 2 ions on the product side, really what that means is the math, like we just did, will come out exactly the same for everybody. So you do the exact same math in terms of how you would solve for the molar solubility. And we can then, in that case, use the KSP values to directly compare the solubilities of each of these. Remember, again, in this situation with KSP, solid on the left, aqueous ions on the right. That means that if we have a large KSP value, that means that we will mainly have products, and we would expect it to be more soluble. If we have a small KSP value, that means that's a small K value. We would actually have more reactants than products, and we would actually expect it to be less soluble. So if you look up on a table the KSP values for each of these, you will find that calcium sulfate is the most soluble of the bunch, would have the larger KSP value in comparison to the other two. And you would find silver iodide is the least soluble of the bunch by looking at the KSP value. So you can only, in a situation like I just showed you there, that you're comparing sort of apples to apples, they're both breaking apart into the same number of ions. You could look at the KSP value, and you should have a fairly good idea which one should be more soluble. Now, when you do not have something that breaks apart into the same number of ions, can you still use the KSP value? And the answer is actually no, you can't. So this is an example of a table. I think you got a similar one in your book. When you do not break apart into the same number of ions, so if we look at these guys here, copper 2 sulfide is going to give you a copper 2 ion and a sulfide ion. That is 2 ions there. When you look at silver sulfide, that's going to break apart into 2 silver ions and a sulfide ion. that is 3 ions there. And obviously here with our bismuth, gonna break apart into a bunch here. Get a couple of Bi's, 3 pluses, and 3 S2 minuses, right? So you get about 5 in this case. So because these guys do not break apart into the same number of ions, that means when you would set up, for example, an ice table and solve for the molar solubility, like we did in the previous examples, you got to do some different math and it's not going to come out the same. So you cannot directly compare it. So as you can see from this table, if we were just strictly looking at the KSP values, we would see that the copper 2 sulfide has the larger KSP value. And obviously here our bismuth has the smaller KSP value. So if you went strictly on KSP values in this situation, you would say that this guy is the most soluble and this guy would actually be the least soluble. When you actually do the calculation like we just did there with the ice table, this is the solubility that you actually get for each of these guys. And what you see in this case is it's actually opposite. It is actually our bismuth that is the larger solubility. And it is our copper 2 that has the lower solubility. So this illustrates a really good point that if you are trying to compare two things that, again, do not break apart into the same number of ions, and you want to know which one should be more soluble and which one should be less soluble, you actually have to do the calculation in those cases. But if they do break apart into the same number of ions, you don't have to do the calculation. You can just go by the actual KSP value. Any questions on the differences there? Yeah. So again, in this situation, you would not want to look at the KSP value. Yeah. All right. As I mentioned earlier, there is a lot of factors that can affect the solubility of something as to, again, whether or not, for example, you would see the solid form. Again, even if the solubility rules say you should see a solid, there are a lot of things that can really affect that solubility or that precipitate actually form it. One of the first things that can affect solubility is what is known as common ion effect. We talked about common ion effect when we talked about buffers. The presence of a common ion, if you remember, with our acids and bases, our weak acids and our weak bases, was it will basically keep the weak acid or weak base together. Now, the same sort of thing happens here when we talk about solubility. Again, if you think about the way this is set up, we have solid again on the left-hand side of the arrow, aqueous ions on the right, which means the only place, if you look at the equation, that you could have a common ion is on the right-hand side, which means if you have a common ion on the right-hand side, our friend Le Chatelier's principle is going to say it's going to shift the equilibrium to the left, away from this side where the common ion is present. And what that's going to do basically is force that solid to stay together, basically, right? So it's going to decrease the solubility of it. So much like what we saw where it kind of keeps the weak acid together, the weak base together in a buffer sort of situation, when you have a common ion presence, it will actually keep the solid together and decrease the solubility because of the equilibrium shift to the left. So if we look at an example of this, for example, our silver bromide, the KSP here of silver bromide being 7.7 times 10 to the minus 13. So if we look at the solubility of silver bromide in just water, and we do that calculation just like we kind of did previously here, we would take our silver bromide, which obviously we have a KSP value for, so we know it's solid. It is one of those 3 exceptions for bromides, iodides, and chlorides. We will get a silver ion and a bromide ion in this case. Again, the KSP is going to be our silver ion times our bromide ion, and that will equal our KSP value there, 7.7 to the minus 13. Doing our ice table here, we're going to go 0, 0, change, going to be plus S, at equilibrium, S and S. We're going to put that into our expression. That's going to give us S squared is equal to 7.7 times 10 to the minus 13. Once again, we're going to square root both sides here. And that will give us an S value here for silver bromide of, call it 8.8 times 10 to the minus 7. That again is molarity, and our silver bromide in water essentially has a molar solubility of 8.8 moles per liter of silver bromide. If we use the molar mass of silver bromide, which is 107.9 plus 7990 for the bromine, that's going to get us here 187.8. I'll write that right, 187.8 grams per mole. That will get us here. Put the whole number in there. Left out half the number. That's not good. I'll try that again. All right, so it's going to equal 8.8 times 10 to the minus 7 moles per liter. There we go. All right, so I'll take that times 8.8 to the minus 7. So once again here in water, basically the solubility here of silver bromide 0.00017 grams per liter are 8.8 times 10 to the minus 7 moles per liter. First off, any questions on that there? So let's take a look at B here, which is we're not going to have our silver bromide in water, but we're going to put it in with a solution of sodium bromide. So in the second one, in addition to our silver bromide, which will set up an equilibrium, we're going to also toss in there a common ion in this case, and that's going to be sodium bromide. Obviously here, the Br minus coming from the sodium bromide is our common ion that we are dumping into this situation. So the only one that's going to set up the equilibrium here is still our silver bromide. And initially here we have zero of the silver, but the change here is because we're adding the sodium bromide, we do have an initial concentration of Br minus that's going into the beaker, and that's going to come from our concentration of sodium bromide, which is 0.001. So in this case, you do need an initial molarity here of bromide. Much like if you were going to do an ice table for buffer, you need an initial concentration on the right-hand side, kind of the same idea here. Again, the sodium bromide is going to supply that initial concentration of our Br minus. The rest of the ice table is going to be pretty similar. It's going to be a plus S situation, and that's going to mean at equilibrium S and 0.001 plus S. Just like normal, we're going to go into our expression. That's going to give us an S times a 0.001 plus S equals 7.7 times 10 to the minus 13 in this case. That is definitely a small value of K. As we talked about, most KSPs are pretty small values. And when we have a small value of K, we could also do a assumption. So you can assume, just like we did previously, that in this case, S is equal to 0. And again, it works the same way as we do with the X's. We can't get rid of all the S's. It is only the one you're going to like add it to a number in this case. So that would get us S times 0.001 equals 7.7 times 10 to the minus 13. Once again, we're going to divide in this case. So we'll go 7.7 to the minus 13 divided by 0.001. Going to give us an S, which is 7.7 times 10 to the minus 10 moles per liter, which once again would be our molar solubility. We also could multiply it by the molar mass from the periodic table here of silver bromide, and that will convert us into grams per liter. And that gives us here a lot of zeros. That gives us, I can go this way, I think, 1.45 times 10 to the minus 7 grams per liter in this case. So this again would be the molar solubility of our silver bromide with the common ion. And obviously this would be it in grams per liter in this case. What we see when we compare without the common ion to the common ion is we are much more soluble in water than we are with this common ion, right? That's 0.0060, right? 145 grams per liter. And we can even see it with our molar solubility as well. We're much more soluble with water than in the presence of common ion. Once again, the presence of this common ion here is going to cause the equilibrium to shift to the left. And that is what's going to keep that silver bromide together and lower its solubility than what you would see in water. So typically speaking, if you have a common ion, it is typically going to be less soluble than it would be in water by itself without the presence of that common ion. Any questions on that there? All right, so why don't you try one here? The KSP of silver chromate is 9 times 10 to minus 12. What would be the solubility of this compound in a solution? Okay, so let's take a look. So again, we are given the KSP, so even if you're not sure about solubility rules, you should know this guy here should be a solid. So we'll start with just breaking it apart into its proper ions. So we got a couple of silver ions here, and it looks like maybe we get a chromate there as well. That's going to give us a KSP here of silver. Once again, we do need to square it because of the coefficient, and we are going to times it by chromate here. That is going to equal our 9.0 times 10 to the minus 12. Going to do our ice table here. Initially, we have 0 here, but we are not in water in this case. We are in a solution that does contain 0.1 molar potassium chromate. Potassium is +1, chromate's -2, so that is potassium chromate right there. That is a salt that's going to completely break apart into a couple of potassiums and one chromate, which I'll just go over here. It is a 1-to-1 relationship between the whole thing and chromate. That means the concentration of chromate in that solution would also be 0.1 molar here from our potassium chromate, as it does break apart into a 1-to-1 relationship. Any questions on that? Again, if you zero it out here, you're doing basically this guy in water, right? So here we got to make sure we're doing it in our common ion. Change going to be, this does need to be a plus 2s once again for the coefficient and a plus s. That means at equilibrium here, we got 2s and 0.1 plus s. Any questions so far here? We're going to put it into our expression. So that is going to get me 2s here. And I do again need to square it as I'm going into here. That's going to be times 0.1 plus s equals 9.0 times 10 to the minus 12. Once again, that is a small value of k. So I'm going to assume s is equal to 0. Once again, it is just going to be the s's we're plussing it from, as we talked about previously with x. Obviously, if you start at 0, whatever you get is significant, so you can't obviously get rid of all of those. That's going to get us something like 4s squared here times 0.1 equals 9 times 10 to the minus 12. However you want to do it, you can multiply these guys together and then divide, whichever way you want to do it. So we'll go 4 times 0.1, which is 0.4, obviously, here, if you do that. So we're then going to take 9 to the minus 12 divided by 0.4. That's going to give us s squared is equal to 2.25 times 10 to the minus 11. Obviously, at this point, we're going to square root both sides. So a little square root action. Kind of get us here. Call it 4.7 times 10 to the minus 6. This again would be the molarity or the molar solubility here of silver chromate in a solution of potassium chromate. Once again, though, we are looking for grams per liter since I added that on at the end. So that would mean that we would take our 4.7 times 10 to the minus 6 moles per liter of our silver chromate. We would obviously need to go to the periodic table to get the molar mass. So that is 2 silvers at 107.9 plus a chromium at 52 and 4 oxygens at 16. Gonna get us here a molar mass of about 331.8 grams per mole, which we could then multiply obviously by 4.7 to the minus 6. And that'll get us something like 0.0016 grams per liter. Once again here, very low solubility in the common ion in general. Yeah. Any questions on any of that there? Questions on common ions then? All right, I think that's a good place to lay